you can go back and check out my answers if you need to look at them again and study. If you're kind of too sleepy to follow along, you can come back later when you're a little more clear-headed. What we'll do today is we'll go through a PowerPoint, just maybe 10 slides, maybe 5 or 6 slides. And then I'll take questions on the homework. And then I've got 3 examples that I show in a spreadsheet, but I just wanted to show you different energy units. And so addressing exactly what you were asking, Marie, about, what units and what constants to use to do these problems. Okay, so let's get started with the share. Okay, so this is part 3 of the USHAG and K analysis. And so we've done USHAG and K. We've calculated all of those various energy terms and entropy term and the equilibrium constant. We looked at that last time. And so let's just talk about equilibrium and how it's how the Boltzmann distribution of quantized states will give us the equilibrium constant, and like which side of the reaction it is weighted by the Boltzmann distribution. So let's look at that. So here's some conceptual examples of chemical equilibrium. So one of the things that you can do, and we've seen this with the Boltzmann factor, is we can change the temperature. And so down here we have a system at a low temperature or lower temperature. Okay, and we increase the heat, we put energy into the system. And naturally, what you see is if these are the individual Boltzmann factors, right? Like this is e to the minus E1 over KT, right? You can calculate those Boltzmann factors as we increase that temperature. Then this factor shrinks relative to all of these other factors. And so now we have a more gradual fall off. So what these blue bars kind of represent is a sideways plot of the size of these Boltzmann factors. And this area under the curve is Q. That's the sum of all those Boltzmann factors. And so as you increase the temperature, Q is bigger. And so we have more options. We've increased the entropy because we've increased the temperature. And you can see there are more molecules or ions or particles in the higher quantum states. And so this is the response of the system to heat. Notice what doesn't change with heat. The spacing of the energy levels didn't change. So the E sub I only the population changed. The E sub I didn't change. So each of those energy levels, notice in all of our energy equations, like the particle in a box, there's no temperature. The only place temperature shows up is the Boltzmann factor. Is how those energy levels are populated. So that's an interesting thing to think about. The temperature doesn't affect the quantum system. It just affects how many quantum states are populated. Okay. And then what about responses to work or compression and expansion? Just a second, I'm moving my windows around. Okay, so down here at the bottom, we have the system kind of like last time. We had our quantum system here. We have the Boltzmann factors plotted in blue. And what happens when we squeeze the system? So we compress it. So we do work on the system. So this is supposed to represent like a gas volume inside a chamber. Okay, this is the back wall. Okay, and this is the gas. And so we squeeze on it. So we push that gas into a smaller volume. So delta V is less than 0. So it's a negative delta V. So we squeezed it, and now it's in a smaller space. Well, we have the size of the system in almost all of our energy equations. Let's just think of a particle in a box. Okay, this is in one dimension, volume's in 3 dimension, but notice that the volume is in the denominator. So when we shrink the box, the denominator gets smaller, and each of those individual energy levels gets farther apart. And so this gap increases. Okay. And so what we have is we have a smaller Q. So this Q, there's lots of energy levels populated. So we have a smaller partition function. We have partition in fewer numbers of energy levels. And so think about the reverse reaction. So the reverse reaction would be the expansion of the gas. So this is compression. And this is expand. And expansion is spontaneous because of Q. We're increasing Q, which drives the equilibrium constant forward. And so the expanded gas would spontaneously occur. Okay. And then we can use that expansion of a gas to push this piston, which could drive a crank, which could turn our cars, drive shaft and our back wheels. And so that's how we use this expansion of gas. And also the changes in temperature to populate higher energy levels. And this is how our engines work. So we're using this population, this statistical population of energy levels to create all of our engines. Now this idea of a density of states, if we look down here, this has got, if we just take this unit here of energy levels, we've got 1, 2, 3, 4, 5. If we take roughly the same unit of energy here, or we've only got 3 energy levels there. And so here we have 3 levels per energy at top, down below we have 5. And so the lower state has a higher density of states. And so that's what we're talking about. This density of states is a good mental concept. If you have a high density of states, you're probably going to have a high partition function and a high entropy. Now let's put these systems together. So here's an example of an endothermic reaction. So we have R for reactants and P for products. But the neat thing about nature is it really doesn't know what a reactant is or what a product is. It just knows about the quantum states. And so notice how these bars decrease, as you might expect, with the Boltzmann distribution. As you go up in energy, the bars get smaller and smaller because you have smaller and smaller Boltzmann factors, E to the minus EI over KT. But notice how this blue energy level is between the 2 gray ones. And notice how this bar here is intermediate between this one. So you just throw this system together and let it come to thermal equilibrium, and essentially nature will calculate all of these Boltzmann distribution pieces. And then this piece right here is Q for the products. And these gray pieces here are Q for the reactants. And so if K is equal to Q products over Q reactants, can you see that this is a small number over a large number? And so that's going to be less than 1. And since it's less than 1, then we're going to have more reactants than we have products. So hopefully you can see how this would give us our equilibrium constant, this ratio of partition functions, that nature is going to come to thermal equilibrium. And if you were to number these from from largest to smallest, it would be, 1, 2, 3, 4, 5. And instead of doing 6 on the reactant side, 6 is over here, 6, and then 7. This is close to 7, so we'll still say 8, 9, 10, 11. So you see, we're numbering largest to smallest, and this 6 is inserted between 5 and 7. It's the next level. It just happens to be a product, but nature doesn't know what's a product and what's a reactant. It just lets these quantum states be populated. Okay, let's look at a situation where we have a higher density of states in the products. And if we number these from largest to smallest, we have 1, and then the products is 2, 3, 4, 5, 6, and then we get to a reactant one, 7, and then 8, 9, 10, and then 11, and then 12. So notice how all of these are on the product side because there's just more energy levels on the product side. Then if we calculate Q, this is a kind of a small Q, and this is a big Q. Okay, so we have a large Q on the product side and a small Q. Even though we have this really large one in the ground state. And so we would have K is equal to Q products over Q reactants. And this one is greater than 1 because we have such a large product Q. Now, if we were to calculate the energies of these, notice that this is the energy of the reactant. This is the energy of the product. It's endothermic, but it's spontaneous. And so this is how you would get a spontaneous reaction with an endothermic system, is to have a large entropy, which is related to Q in the product side of things. And so now let's look at those examples like we did in class. So let me take your questions and then we'll do a couple of Excel examples.
Okay, and these are questions on the homework you're asking?
Yes. Mm-hmm.
Okay, yeah. So I have a few questions, but I'm sure other people do too. So okay. I guess I'll just start with my first.
Yeah, you start off. Yeah.
Okay. So question for number 1, I went through the process like we did. I got my Q, but then for I got my Q number 1 and number 2, I got my Q and my probability, and everything looks correct. But for 3 and 4, for the partition function and the probability of being in the ground state for the product, I must have done something wrong because when it comes to my probability, I got my Q and my probability for Q, I got 0.48 and 0.97, which would give me 48% and 97. And that doesn't work out because it's got to add up to 100, right?
Yeah. Yeah.
And what I was going to say is my B, but the Boltzmann function came out to be 1 because the spacing between the energy levels for the product is 100 wave numbers as opposed to the 200 wave numbers for the other one, which was kind of like one of the examples we did in class. So I'm not sure what I did wrong on this one.
Well, it just depends on how you calculated this product one. Did you set, if you'll notice here, this level is the ground state for the product, but it's not at 0, it's at 100. And so this is kind of a weird situation where the partition function is actually less than 1. You know, I would say that the partition function must be, you know, the minimum value is 1. That is if your ground state has 0 energy, right?
Mhm.
But if your ground state is got like 100 wave numbers of energy, there must be some other place that's 0, right? So in this case, the 0, the level with 0 energy is the reactant state. And so the product is 100 wave numbers and 200 wave numbers. Notice the partition function for the product is 0.997. So it's not 1, it's close, but it's not 1. And then let's see. So I get a 61% chance of being in the product state. I mean, in the ground state, and I guess I didn't ask you the other one because they're going to add up to 100%. But
Yeah, I got, so for the Boltzmann distribution, for the first state, I got 0.62. And now this would have been a rounding for me.
Okay.
But for the next state, I got 0.38. Now, like I said, that could have been rounding. And so the 0.9979, I think that's what I got. And I simply, because I did a rounding. So that makes sense. But then.
But see, you didn't get it wrong because of rounding, because I give it like a 0.05 here for the range. So you could have gone to 10, you could have gone to 104 or down to 95.
No, I haven't submitted my answers yet.
Okay.
Yeah, I haven't submitted yet because, and so.
You mean it didn't add up to 100 because of rounding?
Yes,
okay.
Exactly. For me, it added up to 100 because I rounded up, but the answer I got is is exactly your answer right there. So I did that part right, but then how come when I go down to the, to get my Q answers and the partition function, I get my probability, I end up with more than 100%. I end up with 48% and 97%.
Yeah, see, something's wrong. I don't know. I mean, it's just your individual Boltzmann pieces divided by the partition function for the products. Let me see if I can create this system here. Let me move my screen around. So let's find the wave number example. Okay, so we've got one similar to this. Let me compare it to this one. Okay, so 0, 200 and 100, 200. So let's look at that. I'm gonna copy this over. Oh, that's not what I wanted.
So
okay, so I need to just make this one 100 and 200. So there's our 62% and 38%.
Okay, and that's that. I got that part.
There's
right.
our Boltzmann factor. I mean, that's our partition function. So this is essentially checking the work on the homework. So I have room temperature. I'm using this version of K, which is Boltzmann's constant divided by the speed of light in centimeters per second and by Planck's constant. So.
Yeah, it's the reactant I got right. And in fact, my answers for the products were good until I got down to the probability. Sorry, I'm looking. So
you're saying you get it like a 45 here instead of a.
Yeah, so the partition function and the probability, I got so let me do it this way. So for my energy divided by KT, I did 100 divided by, 0.695 times 298,
Mhm.
and I got 0.48. And then 200, which is the next energy level, divided by 0.695 and times 298,
Mhm.
and I got 0.97. And so,
You got 0.97 here? That can't be right.
yeah, maybe that's why I'm having so many problems.
Yeah. Is your degeneracy 1?
Yes.
Okay.
Yeah, that's the thing. I got to use a degeneracy of 1. So 200.
Well, I mean, you'll have on the video essentially all of this table. And so you can find your calculation error when you compare, if you want to find it later, you can do that.
Okay. Yeah. So I'm not
I'm
sure.
going to make these left justified so that you can see the formulas. So,
Yeah.
okay.
Okay. Yeah.
You can see this. This is the degeneracy times e to the minus energy divided by k divided by t. I've got t and k in different order, but it's still the same thing, k and t. And so that's my Boltzmann factor. And it should be 0.38, not 0.9 something.
And
then the sum of those two is your partition function. And then the probability is just that piece to the left divided by the partition function. And this is the same thing, next row. And so that's why, both these pieces went into this sum. And so by the definition, they have to add to 100% because there's only 2 pieces. So you get this piece over the sum and then this piece over the sum. So there's got to be some problem with your e to the x calculation.
you know what? I think I know exactly what it is. I left something out. I know that's
a negative sign, maybe.
That's what it is. I left I left a big part out. Okay.
Okay, great. Excellent. Okay. And so then we can go down, if we're dealing in wave numbers, then of all of our energies and everything, and they can be calculated in wave numbers, they can be calculated in joules. It doesn't really matter. You can just use, but let's see, what did I ask on the homework? Did I ask for wave numbers for all of these?
Yes, everything is in wave numbers and Kelvin. And so I'm sure other people have other questions, so I'll let other people ask. But when it comes to those next ones, the ones you have right now on the screen, I'm stuck there too. So
okay, so let me pull this aside. What we'll do is we'll do a side by side. And so here we have our internal energy of the reactants. And so here's our internal energy of the reactants. And if I make that left justified, we can double click it and see what that is. Essentially, I did each Boltzmann factor is sum product, because each Boltzmann factor times each energy divided by the partition function. So if you look at that equation, it's a sum of all of those pieces, but the partition function's in the denominator of all of them. So I can do a sum product, which is the energy times the Boltzmann factor piece, and then just add all of those up and divide by Q at the end. So that's what I'm doing here.
Right. No, what was actually throwing me off for all the next series of questions, and it's just one question, and once I figure this one out, I think I'll be fine. It's that you're wanting the answers in wave numbers times Kelvin, all in the denominator. And the problem is for R, all the different constants for R, whether it's K or R, have joules and moles. So I figured, well, okay, I'm sure I have to multiply something by Avogadro's number and all, but the problem is to try to find S and then H, I have to use R. Well, you want the answers in, centimeters times Kelvin in the denominator. And no matter what I try to do, I can't eliminate the joules in R, and I can't eliminate the extra moles if I multiply by Avogadro's number, and I can't eliminate the extra Kelvin.
Yeah, I got you. I understand. So look here though. So in this equation for entropy, that's one of your examples. So here we have that U over T. So you can see on the screen, U is E16 and T is C8. And then plus R ln Q. Well, R is whatever, this essentially is R or K. So
Oh,
whatever, units you want, like this is wave numbers per Kelvin. You could have K, Boltzmann's constant, be joules per Kelvin, or the gas constant, joules per mole per Kelvin. So you just pick whichever the appropriate version of K is.
oh,
Yeah, so that's
okay.
it. That's all it is. Yeah.
Okay, because I was sitting there trying to multiply by moles and use,
Yeah.
I was,
Yeah.
it took me,
No,
I out.
that's why I left them all in wave numbers. I was trying to make it easy on you guys. But yeah, if you miss this part, then all of those are going to be way off, obviously. Yeah.
Okay,
Yeah.
that completely changed. Okay, thank you. Those were
Yeah.
for now my questions.
Okay,
Thank you.
perfect. All
Sorry to
right. And
dominate the
so, no,
conversation.
that's good. It's good to get us started. And so then we calculate the internal energy of the product. So let me scoot over here. 138. Yay, we got that. Here's the entropy of the reactant, 0.4. And then here, let's see, we'll probably do the product. Yeah, 0.46, rounds up to 5 on my scale. Enthalpy of the reactant, enthalpy, 262. Enthalpy of the product, 345. The Helmholtz, negative 67. Okay, Helmholtz over here is rounded to 0. So let me go ahead and increase the number of digits I'm being shown. Yeah, okay, that's beautiful. And then we get to the Gibbs energy, 140 here for the reactants, for the products, 208. And then we get into the fun stuff, the deltas, right? So the change in Gibbs free energy for this reaction comes in at 67. So we could take this 208 and minus 140, and we end up with that. So I just calculated these over here. So here's our delta U's, SHA. So delta U shag here is 67. So that's 208 minus the 140. And then I went ahead and calculated it just to show you that you can get it also with this delta H minus T delta S. So we get the same answer. So that's a way to check your work. You should get the same answer whether you calculated delta H minus T delta S, or just take the two G values and subtract one from the other. Okay. Now, let's see. The equilibrium constant for this, okay, since we've gone up in energy level, we haven't increased the degeneracy and so on, it's probably going to be dominated by reactants. And so we're looking probably for an equilibrium constant that's less than 1. And sure enough, it is. So you can calculate this one two ways. You can calculate it using delta G. So let me double click that. So I have the exponential, or e to the minus delta G over KT. So this is K and T down here. So that's the equilibrium constant calculated using delta G. You could also take the ratio of the partition functions. And so this is the product's partition function divided by the reactant's partition function, get the same answer. So that's great. And so is the forward reaction spontaneous? Or so true, false? And so it's false. It's not spontaneous. The reverse reaction would be spontaneous. We have a positive delta G, so it's not spontaneous. And then we have a positive delta H, and so that's endothermic. And I would say this needs to be endergonic. So that's how you would say it for the delta G of this reaction. It would be endergonic. The delta H would be endothermic. So that's essentially the homework. Yeah, that's the whole thing, is this one big problem. Now, let me show you on Excel other modifications that you might see in these kinds of problems. So what if we had, so this problem for the homework was in wave numbers, right? Look at our energy level diagram. It was in wave numbers. Let's just do another one with wave numbers, only this time look at the products. They have the same ground state as the reactant, but now higher energy level has dropped down. So this would be an example of an expanding system. So we expanded the size of the system, like the room or the particle in a box. We expanded the box and the energy levels crushed down a little bit. And so this would be the compressed state. This would be the expanded state. And so let's look at what happens to the equilibrium constant. So all of this other stuff is the same. You know, they're different numbers, right? The reactants haven't changed. The products have changed a little bit. Now, all of a sudden, we're exothermic. Okay. And exergonic. Okay, so it's spontaneous expansion, and our equilibrium constant is greater than 1. So we're looking at this situation where, you know, we've got two levels that are closer together, so they're going to have a higher Boltzmann factor. So you look here, the Boltzmann factor for the excited state was 0.38 in the compressed state in the reactant side of things, and in the expanded state is 0.6. So it went from a 28% probability of being in the excited state to 38% probability of being in the excited state. So we have a smaller Q here, we have a larger Q here because we have more molecules in the excited state because it's accessible, more accessible at that temperature. So these are a couple of systems done in wave numbers. Well, what about if we did it in joules per mole? So I think I did this example in the lecture, joules per mole. So here we have 0 and 2000 joules per mole. Now look at our K, our Boltzmann constant. It's really R. It's 8.31 joules per mole Kelvin, and our temperature is 298. So actually, to be like perfect, this would be Avogadro's number times K. And so I'm going to make that a subscript. Okay. Let's go ahead and put R in front of that. Okay, so that's, again, we've got R there. Same kind of system, our expanding system. It's a, you know, I didn't go in and make these exactly the same relative to KT. So they're going to get slightly different results, but the same trends, okay? So we have 0 and 2000 joules per mole for our energies. We calculate our Boltzmann factors. Again, it's that that degeneracy, which is D12. Let me go ahead and do this. Okay. Right, it's GI times E to the minus energy over KT. So that's your Boltzmann factor. Add them up, you get Q, do your probabilities. Then you're ready to do your energies. And notice how these are using that that R value. Here's S. And so that C9 is R. And since we want things in joules per mole, we're going to use an R or a K that has joules per mole for its units. So whatever units the problem's asking for in terms of your energies, go ahead and use the appropriate constant. Now we get to our deltas. So again, it's an expanding system. The partition function increases. The energy decreases because our system relaxed. That means we've given off some energy, some heat. So this is exothermic. And it's spontaneous, it's exergonic. And then here's our greater than 1 equilibrium constants. And so this is going to show that it spontaneously expands. Okay, one more example. This is the same problem, but look at the energy units. So here's my energy level diagram. I have 0 and 2, but they're really small energies. This would be energies per particle. Now, I don't exactly know how we calculate a 2-level system for a single particle, because it's either going to be in the ground state or the upper state. So we got to have more than just one particle in this, but this is the scale, 10 to the minus 21 joules. That would be like that's the sort of the scale of single particle type energies. You know, when we're dealing with moles of particles, I mean, you got huge energies, but for a single particle, this would be the kind of energy scale that we would have. And so for my y-axis, I have the energy divided by 10 to the minus 21 joules. And so this is 2 times 10 to the minus 21 joules. So that's the energy here. So you see this, that's for my energies, I have the ground state at 0 and the excited state at 2 times 10 to the minus 21. Singly degenerate energy levels. Here are my Boltzmann factors. Here's my Q and my populations. So same kind of problem, really different energy unit. So what do I use for my K and KT? I'm using Boltzmann's factor in joules per Kelvin. Notice this isn't joules per mole. This is just straight up joules. And so for K, I need to use just joules, not joules per mole. I just wanted to show you an example where K is just a straight up Boltzmann's constant at joules per Kelvin. So we have the degeneracy times e to the minus energy divided by K divided by T. And that's our Boltzmann factors. Okay, and then all my energies are going to be in joules, joules per Kelvin for the entropy, joules for the enthalpy, and so on. This is that expanding system where the energy levels decrease in their spacing because we have a bigger volume and we have a larger Q, but we lost energy, and so it's going to be exothermic and exergonic. So now these also, since these are individual particle type, particle type energies, if we multiply those by Avogadro's number, we get our reasonable numbers for joules per mole. So you could also convert these to joules per mole. You could divide this by Planck's constant and the speed of light in centimeters, per second, and you would get reasonable wave number values. Let's just do that. So let's do Planck's constant up here. 6.626 times 10 to the, which would be E minus 34. Okay, so there's Planck's constant, and that's joules times seconds. And then here's the speed of light, 3e to the 10th centimeters per second. So we're going to take this value here in joules and divide by Planck's constant. I'm going to anchor that because I'm going to copy this down. And then divide by the speed of light in centimeters per second. And I'm going to anchor that. Okay. And I'm going to give myself a couple of decimal places. No. Let's take numeric. Yeah, so that's 16 wave numbers. So again, a reasonable type energy in terms of wave numbers. Reasonable, what I mean by like it's a, it's what do I mean by reasonable? It's hard to explain. It's in the tens, hundreds, thousands place. It's not like times 10 to the 50th or something. That's what I mean. So when you want to convert an energy in joules to an energy in joules per mole, multiply by Avogadro's number. When you want to convert an energy in joules to wave numbers, just take that energy in joules and divide by Planck's constant. So the joules cancel, and then we end up with seconds in the denominator, and that's actually frequency, okay? And then we divide that by the speed of light in centimeters per second, and the per second and the second cancel, and we're left with centimeters in the denominator. So we end up with that wave number value. Okay, so I'll take more questions.
I have a couple questions about the just exam prep, if nobody else has any questions.
Okay.
Okay, number one, you talked about so you talked about the ensembles, and you talked about the Stirling approximation,
Mhm.
and you talked briefly, about it in one of the lectures I'm looking at here.
Yes,
But we didn't have homework on it. And so for things
right.
like the equilibrium, like the example that you did in class the other day, that's at, the end of the K lecture. And then the stuff I'm talking about here with the ensembles and Stirling approximation and things like that, that wasn't in homework. So what can we expect about those kinds of things in the exam? Because usually, you can definitely study the homework and expect
Yeah,
something
those
like the homework.
those concepts were introduced only for the, I'll show you the exact reason why those concepts were introduced. I needed to show you how the number of moles ends up as a superscript. Okay.
Right.
And I needed to show you that when we go to something like a mole of particles, we've got to count. I just wanted to show you the statistics related to the ensemble, because we end up with that. Let me just pull up that lecture because I'm having a hard time describing it. Okay, so that one is on the delta G. So I think that's part 2. Share part 2. Here we go. This piece here. Okay. I needed to show you where this, let's see. Let me go ahead and share this. Okay, so there's two things that this was meant to show, and one of them was, where did this go? Okay, oh, stupid thing. Okay, this piece disappears, and to get rid of this piece, it disappears because of this, and this was Stirling's approximation. Okay, so that was reason one, that I had to show you this, and the other reason was just to show you how I get you comfortable with dealing with NaK being R, and in the number of moles times Avogadro's number gives you just the number of particles, and how this thing shows up here. So that was reason number 2 that I showed you this. So it was really just to introduce Stirling's approximation, and this concept of an ensemble was just for this slide. Okay. And that was building the foundation for this derivation of the equilibrium constant. So I needed to show these guys right here. So they show up in the equilibrium constant, right? Because normally we write our equilibrium constants for pressure. It would be the partial pressure of C times the partial pressure of D raised to the C and D power over the partial pressure of A raised to the A power, and the partial pressure of B raised to the B power. So this would be a gas phase equilibrium constant. And I just wanted to show you that those partial pressures are approximations of the partition function divided by the number of particles. In aqueous solution, like a concentration equilibrium constant, of course, it would be the concentration of C raised to the C power and D. So those are your products, and you have your reactants. And so I just wanted to give you an idea of where these pieces came from. That was the whole reason for that. Okay.
Okay, yeah, and then of course the last couple of problems that you worked today, the application problems. I guess my question is, I know that what's on the homework, what's in the Kahoots, the Top Hats, and Quizlet, that is all very much, you know, fair game for the exam. And just anything that's not, I just wanted to be sure if you're going to ask anything that wasn't in there, just kind of what to look over. So
no, y'all study the homeworks and you'll do fine. Yeah. So I tailored it really close to the homeworks.
okay, thank you.
Yeah.
I had a question about the lab.
Okay, sure. What do you got?
So for question 13 on the lab, it's asking about the population probabilities of the global and the local minimum. And so on Wednesday, when I was in lab, we were trying to calculate it and we were just getting really, really big numbers that Excel wouldn't show. And so we tried the log method and that still didn't really work. And Parker was trying to help us and we just could not figure it out. So I don't know if we were doing it wrong or like what was going on.
Let's see, where did I save that picture? I took a picture on my phone and emailed it out to the TAs.
We tried doing that and we could have done it wrong, but when we used that, we still got like a really big number.
Well, were you doing your deltas right? I know some people were calculating, like say they got the, let me just pull up I'm going to make a blank slide so I can draw. Okay. And I like PowerPoint better than the Zoom whiteboard. So let me just insert a blank slide. Okay. So, you know, Gaussian's calculating okay, so Gaussian's calculating the fuel, say C2H4, right? And you get for that value a G, right? A sum of enthalpy and free energies. And it may be like minus, I don't know, 110 Hartrees. Maybe more, I don't know. But then you multiply that by 2625 joules per mole for Hartree. Okay. And so now you have a really big negative number. You know, what is that? That's another, let's just make it 100. Okay. So put another couple of zeros on there. 262,500 joules per mole. Okay, this is not a delta G for that reaction. This, you have to add in oxygen and it yields CO2 and water.
Yeah,
so
we
you need
did that.
Yeah, okay. And
And
so
I'm
then
pretty
you
sure we
balance it out.
converted.
Yeah. Okay, how many oxygens do I need? There's 2 there and another, so 3. Okay, so there's my balanced equation. So then I've got these G's as well. And then you get the deltas. So your delta G shouldn't be something this big, but it might still be, you know, negative. So delta G may equal negative, let's just say 300 joules per mole. If I try to do K is equal to minus 300 minus a minus 300 divided by R divided by T, then I'm going to get a huge number. Okay, and this is, let's see, you know, it's essentially, you know, this is E to the minus. Okay. So if I were to type in, I don't know what my calculator can do. Like, do you have a number? What number are you talking about?
Hang on, let me go to my Excel.
See, actually, my calculator can calculate either 300. So
because it's part of the one for like the C2H4Cl2 ones that we had to do. And I guess like the Gibbs free for like each individual one was still really big. And so then when you calculated the delta G overall, I was getting to like it's like the 6th or 7th, like 10 to the 7th or whatever is my delta G overall. So maybe I messed up there.
Yeah, so what, let me find your lab, what you're talking about. So you're talking about, let's see.
But Parker, I know he pulled up his old like Gaussian files and a lot
You're
of
talking
the
about the
numbers.
geometry optimization lab or the thermochem lab?
Oh, the thermochem lab.
Okay. And let's just pull it up here. I want to pull out the handout since you guys are, you can tell me what you're talking about. Okay, so it's one of the discussion questions.
Yeah, it's question 13 on the discussion.
Huh. Maybe, let's see. Report template, okay, that's probably it. This one here, okay. Yeah, so you're setting the 180-degree structure free energy as the reference. Okay, so that will be, you can set that one to 0 and then just take the difference to get the local minimum ones. And then you do your partition function because you've got a 2-level system now. You can calculate it that way. You calculate your probabilities. So what you've got here is two-level system with degeneracy. This is 180. This is like 60 and 300, right? And Gaussian tells you this is, this energy here, and this energy here. And you can set this one to 0 and take this one as, let's call this 1 and 2. You can take G2 minus G1 and get that difference, right? And so there's your 2-level system. Then it's no different than what we've been doing in Excel with 2-level system.
Okay. I'll try and do it that way and see what I get.
Yeah, but do you understand the problem now?
A little, well, I don't know, because I was talking about 13, but yeah, a little bit, I guess, because I wasn't.
Well, see, you can't do 13 without
Yeah,
understanding
12.
this. Yeah, you've got to come up with the energy level diagram. And you got the global minimum here and the local minimum here. And you've got to figure out what energy you want to, what are the energies of these two things? This is the ground state. So this is the ground state, 0, and this is the difference between those two. So
yeah, I think I know what I did. I think I wasn't using the right energies for it.
yeah,
That's
so you've
probably
got to
where it
get your
was.
energy level diagram set up so that you can do the partition function so that you can calculate the probabilities.
Okay, that makes more sense.
Yeah. And then here's the deal. So you've got this next one, the 0 dihedral structure is the barrier to free rotation. So you've got, let me just go up to that energy level diagram. Let's see, that's right here. I've got to quit annotating here. How do I get rid of it? Okay, stop that. Okay, so up here, oh goodness gracious. Okay, so here's your, let me go back to annotate and erase all these things. Okay, there we go. Now, what we've got is here's what I was saying about 0. Here's, here's your bound states. And so this was G2 minus G1, right? You follow me?
Yes.
You calculated the structure of this molecule, you calculated the structure of this molecule. So if this is 0 here, then this is the difference in those energies. from Gaussian?
That makes sense.
Yes or no? I can't tell if you're nodding or anything.
Yes, yeah, that makes sense.
Okay, all right, great. This is the barrier to rotation from this one to here or from this one back down the hill. What it's asking on the last question is this barrier. Okay. So if you calculate that energy, maybe we call this G3. Oh gosh, G3 minus G1, and this is G4 minus G1, right? So you can calculate that if you have structure 4, which would be the zero dihedral angle, then you can take that difference there in energy and then can answer this question up here. So it says the 0 degree dihedral angle is the barrier to free rotation. What is the barrier to free rotation in wave numbers? So I'm just asking you, what is that G4 minus G0 in wave numbers?
Okay, thank you. Yeah, that makes a lot more sense now.
Yeah. Okay. I like this being able to annotate on top of a PDF. That's pretty cool. Okay, so it's 8:56. Y'all are rocking. So thank you for getting up this morning. You can always talk about how, I don't know, let me stop the share. We can always talk about how hardcore we are in chemistry. They closed the university, but who cares, right? So I think we're doing it over here in chemistry. We can get it done. So y'all have a good Friday. Stay warm. Don't drive unless you have to. And we'll see you on Monday. You can screenshot this too if you want. Y'all have a good day.